a second. But essentially, your turbine engine temperature is the temperature that you're actually dictating right outside of the combustor. So you're controlling this through your fuel-air distribution. For given takeoff thrust, one might assume that the mass of the required engine would be proportional to 3/2 power of the inlet of the airflow rate during takeoff. In this case, how would 100 Kelvin increase in turbine inlet temperature affect the cruise? Assume the change in estimated engine mass does not affect the fuel. So let me translate some of this in terms of our equations. So it says that based on this, our 4% is our specific thrust of engine 2 relative to engine 1, which is 1.04 at takeoff. And the 5% fuel consumption is TSFC 2 relative to TSFC 1 is equal to 1.5 at cruise. Let's see. Now, we said that the mass is actually proportional to, the engine is proportional to, that's what they gave you, the air mass to the power of 3/2 at takeoff.
Wait, what did he say?
So this is primarily giving us the characteristic of the engine without us having to compute it, but later on we're going to be computing this. But let's assume that we have that. So what does that translate in my problem is, well, the mass of the engine at 2 relative to the mass of the engine at 1 is equivalent to the amount of air or the flight Mach number mass that's passing through there relative to 1 is to the power of 3/2. And what it's asking you is the range of difference. So find S2 over S1. That's what we really want to find, which is actually straightforward. These are easy problems because then you just plug and chug the equation, which you already have right here. But anyway, so let's solve this. So solution. One of the assumptions that we have to make is, well, P exit here is equal to P ambient. So that's a critical thing because otherwise I have to account for my pressure difference in my thrust equation. So let's make it equal. So what this does to my thrust equation right here, to recap, just makes my thrust in terms of, so if this is equal, this term cancels out. And what do I have? My mass that is going through my engine multiplied by my 1 plus fuel air ratio, my exit velocity that's coming out of the engine, and my flight Mach number that's driven by the aircraft. So by doing that, that's 1. We're going to assume, see this, in this equation, if you remember some of the reaction mixtures you've done, right? What was your fuel to air ratio? On the order of what? Very, very small. And if you remember somewhere here, I probably wrote it, and I told you it's going to be around this much range. I think I did. Right here. Right? So I said 0.058, somewhere around there for jet fuel in general for fuel to air ratio, right? So why is that critical? Because if I go and add 1 plus 0.045, does it really make a significant difference? Not really. So I can assume my fuel to air ratio is very small for this problem that I don't have to account for it. I account for it in terms of my heat of reaction, but not in my thrust equation. It's just 1 plus a very, very small value, so it's not really useful. Another thing is, I'm going to assume at cruise, that my exit velocity is equal to my free stream velocity, which is my aircraft velocity. So at cruise, my thrust is equal to my drag, and I'm not generating any acceleration. I'm just cruising across. Now that's also critical because that's where we can save fuel. So, what do I have? I have the specific thrust at initial conditions is equal to my thrust at initial condition divided by my air velocity at initial condition. Now, that is equal to, by doing this, right here, by doing this, what do I have? I set this to 1. And if I'm dividing it by the amount of mass of air, because I'm looking at specific thrust, well, that's going to equal to my rate of change of UE minus U. Now, at initial condition, the aircraft is at rest. So what is that velocity? 0. Unless there's a little bit of gust or something they want to account for, but it's going to be very, very small. It's not going to make a difference to the engine. So it's at rest. So from that, what that tells me is, well, this is constant. Now, let's go to the ratio. I already have my specific thrust ratio between engine 2 and engine 1, and I have it as 4%. So what that's going to translate to me, if the initial thrust is nominally similar and constant, therefore, I could take my mass ratios and relate it to this. So the amount of mass of air that is going into my engine for engine 1, so 1, divided by MA engine 2 at initial condition. Because you've got two different types of engines that are on the same exact aircraft, but one is running at a specific thrust that is different than the other by 4%. So I could relate it by just looking at the amount of mass that the compressor is going to suck in air through my engine. And that's going to equal to, again, 1.04, like we just said. And from that, if I know this, I could go and say, well, my M for engine 2 relative to engine 1 is equivalent to MA at, this is 2 versus 1, so this is 2 versus 1 to the power of 3 over 2. This is a characteristic that they gave us in the problem. So by doing this, what do I get? I get it's 0.943. Now knowing this, I could find the mass of engine 2, and that's going to equal to, because I already know mass of engine 1, which is 4,000, this will equal to 3,772 kilograms. So, and mass of engine 1 is really 4,000 kilograms. So these are the engine weight that you have within your aircraft, and they're two different engines, and now you already got the mass for engine 2, which is running hotter than engine 1. So from that, I can go into my specific the distance traveled ratio that I need right here. Let's write it out. So I want S2 over S1. So that's going to equal to velocity 2 over TSFC of 2 relative to, I'll make this longer, velocity 1 over TSFC of 1. L over D, 1 over gravity, multiplied by the natural log of M2 at station 1 relative to M2 at station 2, which is the final condition. The natural log of M1 relative to station 1, M1 relative to station 2, the initial mass relative to my final mass. So, as assuming that now that I scale my engine smaller, that my velocity for 2 is equal to velocity of 1. But yet, so the travel of the aircraft is the same between both conditions. I'm just running a smaller engine at a higher max power. And I'm trying to evaluate the difference between the distance traveled for both. Now, the aircraft is the same. I'm keeping the same aircraft. The gravitational force is the same. So what do we get? So what do I have? I have the same type of aircraft. I'm on Earth, I'm not on Mars, so the gravity or moon, so the gravity is the same.
Mars.
So what do I have? I have S over 2, that S2 over S1 is equal to, my velocities are equal because I'm trying to keep my same terminal velocity of the aircraft.